I'm Sarang. Here is the agenda for today's session. We'll touch upon Spark components and its architecture. What are some of the different deployment modes in Spark? What is PySpark shell? This will be our first interaction with Spark shell, and we'll also learn how to submit a PySpark job. Post that, we'll explore once we submit a job, how to see that on the Spark web UI, and what all details do we get pertaining to a job that's running in the background. So first is the set of problems that we learned were faced at Yahoo, and why did they have to switch to Spark, wherein they wanted to have dynamic content and personalized advertisements targeted at users. To achieve that, they started using Spark because when they were using Hadoop, they were able to achieve some of the benefits of big data, but then in order to get to a state wherein they could do real-time analysis, they preferred Spark over Hadoop. The problems that they were trying to address were operational management, training, and business monitoring. So, all through a single data set, but with different objectives. The data collected by eBay was 500 terabytes a day. At that point in time, it was 10 terabytes a day. And the main reason for Yahoo switching to Spark was their observation because of the increase in data, there was a lot of latency in processing it, and they wanted to avoid that latency. So, late processing of data was the primary concern at Yahoo. Similarly, eBay has been using Spark, and if you look at some of these stats, they have 8.8 million new listings every week. So that's a huge volume to address every week. And they also claim all this arises because of huge volumes of data and the time involved in processing that data. So they have been using Spark at eBay to address many of the problems related to latency. And these are some of the details around the cluster and the data pipeline that's there at eBay. So they have Hadoop as a basis storage and a Spark for processing. Using that, they were able to convert an ETL process to almost near real time that earlier used to take between 1 and 2 days. And eBay's analysts are now able to leverage these clusters. Now, the size of the cluster is quite massive, 2000 nodes, 100 terabytes of RAM, 20,000 cores, and there are several developers that are writing multiple domain codes helping through complex data modeling and data scoring using this cluster. And they have Kafka as the messaging system as part of their cluster, Spark Streaming for near real-time analytics, and Spark SQL for data preparation. So let's see how Spark would fit into Hadoop ecosystem and how it is useful with Hadoop. So there has always been a myth when you're working with Spark. People will say, so are you using Hadoop? You would say, no, I'm using Spark. And then at times people will say, no, I'm using Hadoop as well as Spark. So first of all, much of that confusion will get clear once you understand where does Spark sit in the Hadoop ecosystem and how do we use it. And if you haven't tried installing Spark on your own, so Spark comes with two different options in majority of the cases. Whether you want to set it up with Hadoop or you want to set it up without Hadoop. So only once we look at what are the benefits that are made available by Hadoop, we'll be able to understand whether we'll require Spark with Hadoop or without Hadoop. So Hadoop ecosystem looks like this. Everything sits on top of Hadoop platform and there is a management component involved as well that helps us manage this entire ecosystem. And the entire ecosystem is then classified into five broad categories. The very first one is the batch processing libraries that help us perform batch processing on data that's already been received or it could be historical. And we have several libraries for that. Now, MapReduce version 1 and version 2 were made available with the versions of Hadoop. Followed by that, we had Pig for data analysis, cascading again for the same purpose. Now we have a Spark that claims to be 100 times faster than Hadoop. And followed by that, we also have Taze coming up. That's also trying to catch up on this space and claims to be a bit more faster than Spark. All these categories keep on improving every day. There are newer tools coming up every day for a specific purpose. There are even big data tools that claim to be very good in big data processing as long as data is in time series format. That means there is some date and time factor involved with every record that's showing up in your database. So there are specialized tools for a specific kind of data as well these days. So coming to the second broad category, we have machine learning and graph analytics. Now, for machine learning in Hadoop, we earlier had Mahout, and in Spark, we had MLlib, and now it is only ML that has further improved. We also have graphics available as an engine in Spark that helps you convert your data in the form of a graph, wherein you will have vertices and edges so that you can perform correlation analytics. Now, this is very much similar to kind of recommendations that you see on LinkedIn. So, LinkedIn has graph database in the background wherein if you and I are not immediate friends, but one of us has a common friend, then we get to see each other as a recommendation. That probably you might know this person as well. And the reason is our skill sets could match. The companies in which we have worked could match. Our qualification could match. Our name of university could match. So all these are properties associated with us. And we are represented as a vertex in a database system, and all these are properties and correlations happen on based on the properties. So that kind of behavior is also possible in Spark if we use the graphics module. Coming to the third category, SQL, and this is again a very important topic. Many of us would have worked either as a database developer or as an application developer, or for some other reason, we have to get back to database for persistence, wherein data has to be stored in some form so that it can be referred later. Now, before the introduction of big data or tools like Hadoop and Spark, often the process of analyzing data was the file has come in, analyze the file for the structure, and if the file is to write some scripts to load it to a database, load it to a temporary table in the form of a string, and then I would say a list of strings wherein every string was a record. Then split the file, do some data quality, data analysis, convert that to a relational table. Then the third step was to again create a new table and convert all the columns to respective types. So if there was a date, do a date conversion. If there was an integer, do an integer conversion. At that point in time, the data was available for analysis. And this took very long time. Now with the Spark SQL kind of tools and Hive kind of tools coming in picture, we just have to point these tools to files either in HDFS or in cloud storage and say, go and infer the schema. We are not going to tell what is integer and what is date. And then all you have to do is start writing SQL commands. So without us loading data into database and doing all the analysis, with the power of big data, we have the ability to analyze that data without going through all these steps of data conversion. That would take a significantly long time for us to confirm what kind of data it is. So in this space, we have a Spark SQL as the module and the equivalents of that in Hadoop for Impala and Hive. There were tools for NoSQL data analysis and searching NoSQL data like Solar and HBase. However, that hasn't changed as part of the Spark ecosystem. So if you have to still refer these tools within Spark, so one option is you can use a Spark SQL that has the ability to read JSON data as well. That's NoSQL data. And if not, you can still use these tools in combination with the Spark. So Hadoop was well known only for batch processing. It could not do real-time processing. But Spark came up with a module dedicated for streaming and real-time analytics wherein, and that made more sense because you don't require tools that only have the ability to analyze historical data. What about the new data that keeps coming in every day? So to address that, we had a Spark streaming and then we have a new tool as well these days that's popular called a Storm. And a Storm is the one that I mentioned is better referred for real-time data analytics. Now, all of these libraries and tools that are part of the Hadoop ecosystem, they all are ported on top of Yarn as an execution engine. So Yarn stands for yet another resource negotiator. And it's kind of a resource management tool that ensures whenever you submit a job and specify the resources to be used for that job, it ensures that the resources are available and are allocated to the job so that you don't face issues executing any of those. Usually, when you will have to set up a Spark on your local system for the purpose of testing, you will require HDFS because you don't have cloud storage on your system. And that's where Spark would have to be set up with Hadoop because you'll have to push files to HDFS to test out your jobs. And usually, when organizations have to try these things out, one option is they should have a development environment on cloud as opposed to production and QA so that the jobs can be tested using cloud storage instead of HDFS, or because storage can be configured to be cloud when working on cloud. So many organizations have an on-prem dev cluster wherein things can be tested internally, and that's where they prefer using HDFS as opposed to having a cloud storage. So Spark works with both, and let's see what are some of the advantages that we get when it comes to using Spark with Hadoop. So the advantages of a Spark, first touch upon all the blue boxes here. First is ease of development. You don't have to write complex jobs like MapReduce, jobs that we had to earlier write in Hadoop, because Spark has made available an object that simplifies a lot of this and it abstracts all the complexity. We call that as resilient distributed dataset. That object internally has fault tolerance inbuilt. It internally has the ability to even convey to the master that a particular block is taking a lot of time to execute, so that Spark cluster can get into the mode of preemptive computing by destroying that block processing and then reprocessing that. In a nutshell, Spark abstracts all that complexity and allows us to only focus on data transformation and data aggregation. So that's where ease of development has been made available by Spark. Second, I mentioned that Spark at times work 100 times faster than Hadoop because Spark does in-memory processing. That means whatever you want to process in Spark, it will first be loaded in memory and then processed. So Hadoop also was doing part of that, but then the challenge was if you have to write 20 steps of data transformation in Spark as well as in Hadoop. So when you write that in Spark, data will be loaded in memory once in Spark, and all 20 steps will be applied one after the other without data being unloaded to the disk back or being unloaded from the memory. However, when Hadoop used to operate on this data, it used to load it in memory for a step 1, generate intermediary output from step 1 and save it back to HDFS. HDFS was on your disk. Then second step will consider that intermediary output as input, so load it back from HDFS to memory, process it, again generate some intermediary output for step 3. So the cycle used to work like this until 20 steps. So every time there was data load and unload happening between memory and HDFS. So that caused a lot of time in terms of the latency involved in loading the data. So Spark overcomes all of that, and that is why it is 10 to 100 times faster. It is at least 10 times faster in almost all scenarios. In many cases, it can go at least up to 100 times faster in terms of performance as well. And thirdly, it gives us the ability to combine multiple workflows, wherein many times when we do data analysis, so you might see for one analysis, you have to perform 20 steps. For another analysis, you have to perform 30 steps. But what we observe when we write down all these steps is the data set is same, and between the two processes, there are 10 to 12 common steps. Then why to write two separate Spark jobs to perform those steps again and again? First is you will waste those many resources in terms of cluster usage. Second, you will require more time in monitoring your code, even if that's a matter of just 10 to 12 steps in two different jobs. So often there is an option, and that again comes back to the level of expertise a developer has in terms of designing jobs. So you can also design jobs in a way wherein one job does all these 10 to 12 steps together, and then there can be two split jobs considering the output of previous job as an input, or there could be one single job that forks the process to say, now there'll be two workflows followed by my job. One is for this kind of use case and the other is for the separate use case. And then finally in the end, when you'll have aggregated output from the two pipelines, you will combine them. So Spark supports all these complex kind of workflows to be implemented either as a single job or as a combination of multiple jobs. So these are some of the main advantages of a Spark. And when we combine this with Hadoop, so we come across a few other advantages that are made available as part of the Spark ecosystem. So when you're using Spark with Hadoop, you'll have unlimited scaling, because the horizontal scaling concept that was made available in Hadoop, that has been extended in Spark. So the Spark development team leverages that instead of reinventing the wheel and coming up with something to be implemented from scratch. Second, Hadoop being an enterprise platform, it made sense to leverage that and build something on top of that. And that's where Spark started improving itself on something that already existed. And third, Hadoop supported wide range of applications like Hive, Impala, Pig. So all that is also supported in Spark, again as a virtue of its integration with Hadoop. So when we combine together all these advantages of Spark and Hadoop, we get a very powerful appliance that we are going to learn now. we will take a look at the Spark components and its architecture. So one of the most powerful thing as part of the Hadoop architecture and the components involved herein is the Spark core engine. So everything sits on top of a Spark core engine. This is the core engine of the entire Spark framework. It provides utilities and architecture for other components. So all the abstraction when it comes to processing everything in memory is made available by the Spark core engine. Everything that sits on top of this core engine leverages RAM, and there is again the concept of fault tolerance that comes in. So when we were working with Hadoop prior to Spark, fault tolerance was a feature that was made available by HDFS itself through its distributed storage. But when we switched to Spark and we wanted to process everything in memory, then again came the same challenge as to how do we ensure fault tolerance in jobs that are running in memory. So Spark beautifully combines the RAM of all systems and come up with one distributed memory model, wherein if a data is being processed on, let's say, 200 systems and in their memory, and if one of the system goes down, it knows where exactly the process failed. I mean, if it had to perform 20 steps and if it was at 15th step, it will know that where exactly the process failed at 15th step, and it will have some temporary caching enabled in all these steps in memory again to know that it has to pick up from 15th step and what will be the replicated system memory wherein all this would have to be picked up again, so that it is able to catch up with other datasets that are being processed and does not cause a significant delay in the process on account of failures. So all these are intrinsic features of Spark. We don't have to explicitly invoke them or say turn this on, turn that off. All that is made available by Spark core engine, and all these components, Spark SQL, streaming, MLlib, graph, Spark R, they interface with the Spark core engine, leveraging all those features automatically. So Spark SQL is used for structured data processing, and it can run unmodified Hive queries on existing Hadoop deployment. Spark streaming is used for real-time analytical and for building interactive apps for live streaming data. Machine learning library is used for trying machine learning problems. GraphX is used for having a graph kind of analytics. This is similar to Giraffe earlier in Hadoop, and it combines data parallelism and graph parallelism concepts. So this library again has something built on top of Hadoop on its own to make sure that the graph is the most optimized graph. And then there is support for R language as well. Now all these Spark components, they do have some data structures that automatically work with the Spark core engine, and Spark core engine has one data structure that has all these distributed processing abilities and properties inbuilt in it. We call that as resilient distributed data set. So when we talk of data frames in Spark SQL, we will also see how data frames can be converted back to RDDs, and RDDs can be converted to data frames as well. And data frames internally process everything on top of RDDs. So the best part with Spark is whenever we interact with any of these libraries, each of these libraries come up with an abstraction or an interface that only requires us to focus on data and minimally on configuration. And internally, the beauty of all these abstraction layers is they still get converted to RDDs downstream. So Spark streaming gives us one object called data stream, and data stream is nothing but a collection of RDDs. Spark SQL gives us data frames, and when we process or invoke any commands on data frames, that does the same processing on data as you would do in Python pandas data frame. But then under the hood, everything runs on top of RDDs. And same is the case with ML pipelines that make it easier to combine multiple algorithms or workflows, because workflows are supported in Spark core engine as well. So those are extended to machine learning pipelines. So all this is very logically designed and beautifully at the same time to make sure that developers don't have to break their head over deciding what to use, how to combine, and get down to the most basic level of coding every time. We can just focus ourselves on the abstraction features in every library, and we should be good to try all of these. Now that we have touched upon different components in Spark, so now that we have looked at different components in Spark, we should also explore the architecture of Spark, and that means what's there in the Spark core engine that supports all these modules, and what exactly is a SparkContext. So SparkContext is an object in driver program that coordinates all the distributed processes It is an object and driver program that coordinates all the distributed processes, and we see driver program as the program hosting Spark context that integrates or coordinates with cluster manager. That will be Yarn in majority of the cases, or it could be Spark standalone cluster as well. So cluster manager will provide executors that will be in the form of Java virtual machine processes with some logic. So Spark Context will send the application to executors through the cluster manager, and executors will be the worker nodes. It is actually used interchangeably in Spark, wherein we call executor as a worker node or worker nodes hosting multiple executors. So Spark Context will execute tasks in each executor. Now, this causes a lot of confusion, especially if you look at the Hadoop architecture. So Hadoop had all these concepts of name node, secondary name node, and then data nodes. In Hadoop, name node was the main master node controlling the entire cluster. And since it was a very critical node, anything is prone to failure when you set up an infrastructure. It could be resource usage, it could be power outage, or it could be something else. Power outage is the least possibility. Well, there could be some events that destroy entire data centers. You lose everything. So that's a second thing that we don't need to worry about, and usually cluster admins or cloud vendors need to take care and ensure that our clusters are backed up. But if one of the master node goes down, it can have a significant impact on the cluster. So that is why we had secondary name node, and as the name suggests, if the actual master node failed, the cluster used to switch directly to the secondary master node. And then that name node used to coordinate with all data nodes, and data nodes were the worker nodes. So if you try to visualize this, there will be one master controlling multiple slaves, and each of those slaves will have three main components. One will be RAM for processing, second will be disk for storage, and all of those disks will be combined together on multiple systems to form one giant HDFS, Hadoop distributed file system. And the third component will be the number of executors available, or the number of CPUs available on that system for processing. Based on that, we will have the number of executors. So usually a good rule of thumb is if you have 4 CPUs, you should have 4 JVMs running on that system, wherein every JVM is an executor and one JVM is tagged to one CPU process. When we think of all of this in a Spark context, it all remains the same. It's just that some of these terminologies have changed. So name node is now replaced by the driver program that takes care of taking the applications or executing them through Spark context. Especially if you talk of Spark version 2 onwards, it comes along with Yarn. So Yarn was earlier available as a separate tool for managing the cluster. But then, given its expertise in ensuring that the jobs run without any issues and there are no scheduling issues as well, wherein if multiple jobs are to be run, how it has to schedule the resources and make sure that once a certain number of jobs have completed, the resources are made available to the other without any failures. Because of its properties in managing the jobs and cluster in a very efficient way, it has now been made available as part of the Spark. So when you submit a job in Spark, it can either be run on Yarn or it can be run on Spark's own standalone cluster manager. So cluster manager has the responsibility of taking the application from Spark context and then running that application on different worker nodes. These worker nodes will essentially be the equivalent of data nodes in Hadoop context. But then, like Hadoop, they will not use the disk of all these worker nodes for processing data, and rather it will use the RAM of all these worker nodes put together for processing data in Spark. Now, each of these worker nodes will have some internal components because depending on the number of CPUs, they will have number of executors. Every executor will have a little amount of cache to make sure that the executors are able to manage their processes. In addition to that, there will be certain number of tasks that these worker nodes will be managing. So these tasks will be running on one or more than one executors at one given point in time. And for processing these tasks, there will again be memory or cache, and this is the actual RAM that is used to process a task that will have data coming in. So all these are very important concepts and components in Spark architecture, and also simplified to the extent wherein we don't have to see what is data node, what is name node. We just note that there is one master program, one driver program that gives us a Spark context, and using that context, we should be able to run any kind of application in Spark. So coming to different deployment modes, when we think of this architecture and we have to submit our job, the job has to go to the driver program, and then followed by that through cluster manager to spin up different containers or an app master taking control of the entire process. So when we submit jobs to driver program, it requests cluster manager for resources. Cluster managers will create an app master wherein every program is considered as an application, and every application has a name. So every program or the job that we try to run, we associate a name. We'll say you're doing Twitter sentiment analysis. So you'll say tweet sentiment as your job name. If you are analyzing content, reading a CSV in data frame, so you'll say data frame CSV analysis. So every program that we run in Spark, it's called an application, and we associate a name with an application. And for managing every application, cluster manager creates an application master in the background. Application master has the job of ensuring that the application is running smoothly on different worker nodes. So we don't take data to application in any of the big data programs that we write, but we rather take program to data. Now, what does this actually mean? That means when your data is saved on HDFS, that's a distributed storage. So you'll have to save data once, and that's accessible to all machines that are part of the cluster, first of all. And second, if the data is distributed and accessible to all machines, should we again take data from a distributed storage back to machine for processing? Or should we write a program that can be run on all these machines, referring the same data and ensuring that the data is split or distributed in a way that every machine operates on a unique subset of data as opposed to processing entire data and causing duplicacy? So Spark also extends that concept through application master. Application master will take our program to all the worker nodes, and all worker nodes will operate on their respective dataset that they refer in HDFS. Now, when we submit this job, there are again multiple ways in which we can do this. And for this, I would want to show you something on the notepad. So there are two main modes of submitting job. One is you submit it locally, or second, you submit it through a resource manager or a negotiator like Yarn or Mesos. When you use local mode, that means you say the Spark context as well as the entire application has to run on one single machine. And that means you are just testing your job. So usually when you write a Spark program and before rolling it into production, you may want to test it. Often a common way of testing that is to use it in local mode, wherein you are not harnessing the distributed power of the cluster and at the same time ensuring that your job does not have anything that can lead to crashes. So you will operate it on a very small data set, not on the entire data set that you wish to process, as long as data format is consistent. And then in that case, you will say run on one single machine, have SparkContext or the master or the driver application as well as entire application run on one single machine, and on this machine you will specify number of threads to be used. That means the number of or the degree of parallelism that you want to specify on your job. Now this could be the number of executors that are supported on your single machine where you are running your job. And now coming to the production mode. So in production mode, often you could either have Yarn as the resource manager, or you could have Mesos. That's another tool from Apache. Usually Yarn is more popular, and they both have slightly different set of configurations to support different ways of submitting job. Now within these two tools, there are two different ways of submitting your job. One is you submit it in client mode or you submit it in cluster mode. When you submit it in client mode, that means use one of the or do not use any of the cluster machines as the driver program. So imagine you have set up a cluster on cloud environment. That's a 200 node cluster. And another feature of the cloud is you can have a bunch of virtual machines that can be used to connect to this Spark cluster. So instead of using one of the nodes to access a Spark cluster, you use separate set of virtual machines. So you'll say, let's say another 10 virtual machines on cloud to connect to Spark cluster and submit jobs. Now, in many production environments, this is the standard protocol that you should not connect to any virtual machine in the cluster directly. Rather, have separate set of virtual machines, 10 or 20 dedicated for allowing developers to submit jobs. So when you submit job through this virtual machine, you will say connect to this cluster. This is the address of my cluster, and submit jobs in client mode. That means the virtual machine from which you are submitting the job that will host the driver program, and these are not part of Spark cluster. So that essentially means that until the job has completed and has returned, these driver programs will continue to wait and let your application run. The second mode of running a job is cluster mode, wherein we do not specify the cluster VM to be used as client. So the one that I mentioned was the cloud usage, wherein you can have different set of VMs. The other option is you can also submit jobs in client mode by specifying this data node on the cluster has to be treated as the driver, or this particular node has to be treated as driver. Do not use any of the cluster machines as the driver program. Use any specific machine in the cluster as driver program, or any machine outside the cluster. The second is cluster, wherein we do not specify the any of the VMs that are part of the cluster to be used as client, and let cluster choose or nominate any VM to be used for running driver program. So these are three different ways of submitting a job. One is local, or using yarn you specify whether you want to use client mode or the cluster mode. So some of these examples are actually based on submitting job that requires Java classes, but then the same can be done using Python files. So we will use each one of these using Python files as the input to be executed on PySpark. But then the tool to submit jobs remains the same. You say Spark submit and then say master local. In this case, you have to specify the jar file from which this class has to be referred. But in case of Python files, it will just be the Python file. Then if you want to submit job in the client mode, so in this case, we are saying the node where master is running, but you could just say master is yarn if your cluster supports yarn, and then the deployment mode is client. You can specify executor memory, executor cores, and then the additional files that are required for your code. It could be jar files in case of Java, it could be additional Python files as well. And then when it comes to submitting job in the cluster mode, you will say master is this particular node where your driver program would be running, and then deployment mode is cluster. But then this syntax is slightly old. You don't have to specify always the path to the driver or the URI of the driver node. You can just say master is Mesos, master is yarn. It internally resolves where exactly is the driver program. Thank you.